Hi, my name is Quan Liu, and this is Lab 1, Charge Tapes. So the point of this lab is to use sticky tape to observe the transfer of electrons. In this first picture, this is how we're making the tape, the U tapes, and this process charges it. In the second picture, you can see how the tape will move towards your hand when you bring it nearby. And in the third image, this is how we're going to numerically measure the amount of charge on each tape. So the way we do this is we model our tapes using a single point charge, and we're going to use Newton's second law, we're going to use Coulomb's law, and a bit of Fermi estimation. And our end results are that we have about 1.07 times 10 to the negative 8 coulombs of charge, which is about 0.0000139% of the surface electrons being stripped away. So first, we make two tapes and we dangle them nearby each other, as shown in these pictures, and the tapes repel each other, so that tells us that they are of the same charge. We don't know yet that they're positive, but we know that they are either both positive or both negative, and we do know that if you charge a plastic pen, it will be negatively charged. So when you bring that negatively charged plastic pen nearby this, we observe that it's attracted, so that tells us that the charge on these pieces of tape is positive. So numerically, all we need to do is get the distance between tape A and tape B, and the measured result was 2.3 centimeters. But using this, we can calculate the electric charge, the electric field, the electric force, the electric field force, by using the fact that tape B is floating. And so that means that the mass, the weight, is equal to the force generated from the electric field. So we set these two equal. The mass is the length times the linear mass density, and we also know from Coulomb's law that the force is equal to this constant K times Q squared over D squared. And so we can calculate Q using this. So the charge is calculated, and it turns out to be this number, which I said earlier, and the deficiency, there's a lot of electrons missing from this one piece of tape, but that is a very small fraction of how many atoms there are in the actual piece of tape. We calculated the number of atoms on the piece of tape. 1 angstrom is the diameter of an atom, and we're assuming that each atom takes up a circle of radius 1 angstrom, and so this calculation gives us how many atoms there are in the surface. So that we did make some assumptions along the way. We treated each tape as though it was a point charge, even though it is not, and we assumed that each U tape was made about the same way, so they should have about the same amount of charge, and we're also assuming that it's evenly distributed. Systematically, we can't guarantee that each tape is the exact same, and they also lose charge over time and through handling, so those are sources of errors, but the model is also wrong because we made these assumptions. So what if electrons had positive charge, protons had negative charge? What would change about these observations? Nothing would really change, except that we only decided that the tape was positively charged through using the charged pen, and if protons had negative charge and electrons had positive charge, then we would also assume that the charged pen would be positive. So we would observe the same things, but we wouldn't know if it was positive or negative. We just know the parity. Why is it important to handle the tapes as little as possible? they discharge when each atom interacts with some surrounding atom. So it's not a conducting material, so it loses atoms locally rather than having a pool of atoms that are shared across the entire object. So each place that it's touched is discharged, but it's just that local area and not the whole object.